My name is Brian Strong, and today I'll be presenting my Capstone project, the Privacy Aware Academic Risk Intelligence System, or ARIS. At the center of this project is a simple but important question. How can we identify students who may be at academic risk early enough to help them while still protecting their privacy? That question matters because students can fall behind in ways that might have been prevented with earlier support. But institutions often face the same two barriers. Student data is spread across multiple systems, and privacy rules make it difficult to bring that data together. So even though early warning systems can be effective, many schools still struggle to use them in a secure and practical way. That challenge is what led me to ARIS. ARIS is a privacy aware academic risk intelligence framework built around federated style learning. In this architecture, each institution acts as a client silo. Student data stays inside the local institution, and what gets shared is model level information rather than raw student records. Those aggregated updates are then used to improve the global model. In ARIS, that federated style process is paired with XGBoost, dataset harmonization, and the decision aggregation algorithm to produce advisor ready risk tiers through the dashboard. This slide captures the central idea of the project. ARIS is designed to bridge the gap between fragmented data and actionable student support. By using multiple sources of information while still respecting privacy constraints, that framework creates a path from disconnected records to meaningful intervention. The project unfolded in four major stages: dataset intelligence, federated modeling, decision aggregation, and dashboard development. Over time, it grew from a data problem into a full decision support system. As the system took shape, a few technical ideas became especially important. Federated style learning preserved privacy by keeping institutions in separate client silos and allowing training to happen locally. Federated XGBoost gave the model a way to learn across those silos using aggregated statistics rather than raw student level data. Feature engineering strengthened the predictive signal, probability calibration improved score meaning, decision thresholds determined when risks became actionable, and the decision aggregation algorithm translated model output into advisor facing decisions. ARIS was evaluated using three main dataset conditions: a synthetic dataset for pipeline validation, an academic and performance retention dataset, and a student management dataset. It also accounted for social determinants of education, including attendance, engagement, financial stress, support access, and outside responsibilities. When these sources were combined, the system achieved its strongest performance. To evaluate the system, I focused on five key metrics. Accuracy shows overall correctness. Precision shows how reliable the at risk flags are. Recall shows how well the model identifies students who truly need support. F1 score balances precision and recall. And RLCAUC shows how well the model separates higher risk from lower risk students across thresholds. When I looked at those metrics together, a clear picture emerged. High accuracy alone did not always mean the model was identifying the students who needed help most. The biggest takeaway was that performance depended heavily on feature quality, class balance, and the ability to combine multiple sources of data. Because this project deals with sensitive student information, privacy had to be built into the design from the beginning. ARIS uses federated style learning so raw student records never leave their source institution. There is no centralized storage of student level data, access is limited to authorized users, and predictions are used to support students, not penalize them. This poster summarizes the problem, method, results, and impact of ARIS as one integrated system. These visuals highlight the system architecture, workflow, and outcomes of ARIS. When the system was tested, the findings showed a clear pattern. On synthetic data, the model performed near perfectly, confirming that the pipeline worked under ideal conditions. On the academic performance data set, results were weaker, showing that sparse features and class imbalance reduced predictive strength. On the student management data set, accuracy was high, but F1 score was low, meaning the model ranked cases well, but had more difficulty with minority class detection. The strongest real-world result came from the combined data set, which achieved the best balance across accuracy, F1 score, and RLC AUC. That result becomes even clearer in the RLC AUC of 0.870 for the combined model. That score shows strong ranking ability, meaning the model can effectively distinguish between lower risk and higher risk students. That matters because strong ranking performance makes the system more flexible across intervention thresholds. From an implementation standpoint, ARIS brings together four main components. The Streamlit dashboard, a federated style XGBoost pipeline, dataset intelligence for schema alignment and feature engineering, and decision aggregation for final advisor facing outputs. In the modeling pipeline, institutions operate as separate client silos. Local training happens inside each silo, and aggregated updates are used to build the global model. Because this system deals with student outcomes, ethics is also central to the project. ARIS was designed around data responsibility, privacy, fairness, transparency, and accountable use of results. The goal is for risk scores to function as tools for support, not punishment, and for human advisors to remain in the loop when decisions are made. Looking ahead, ARIS could expand through cross-institutional collaboration, real-time intervention, and more personalized student recommendations. This work will also continue as part of my doctoral research with the long-term goal of growing ARIS into a broader, privacy-aware research framework for academic risk intelligence. Thank you.
Thank you, Brian. So we
Uh-huh.
have 5 minutes left for his presentation. So if you want to do some demo, it's fine. Otherwise, we can go for the question answer session.
Yeah, I actually had a demo I was going to show you right now. Let me go to that real quick. Sorry about that. Let me just stop sharing here. Okay, I have to come out of this. I keep pressing the wrong button here. And let's see. Let's go to, let me see. How do I move this out the way? Okay. Okay, sorry about that. Here we go. And let's go to this. Good evening, attendees. I'm going to give you a brief overview of my dashboard. So as you can see here, this is the navigation section, which I'll cover more in depth in a second. We have the sidebar guide, which essentially tells you about the navigation, the data set, the column mapping, and what the model actually is doing, which basically the model controls training/scoring behavior and the decision threshold tile. Then the model features are explained, as you can see here, the model type, the decision threshold, the evaluation metrics, and the decision aggregation algorithm. And I have a data mode button here that allows you to upload a single CSV or combine multiple CSVs. And there's also a public dataset optimizer button, a threshold booster button. And I want to show you the targeting/label section, which allows you to build a composite at-risk label from observed indicators to reduce label noise, essentially, which you can actually click that, and that will do that. So, and I clicked that, but I'm going to click that off at the moment. Then you have imbalance handling. The model controls are explained, which speaks on the boosting rounds, the histogram bins, the learning rate, the lambda, and the gamma. and the train retrain model button and the decision threshold. And now I'll move into the actual dashboard itself as far as the pages. So you have the overview page, which is the overview of the dashboard, the data set preview. See here, you have the data set intelligence page, which essentially describes the data set, the rows, the columns, missing cells, the target. Then you have the data set intelligence advisor. Basically, it's saying what the dashboard thinks is happening in this data set and what to do next. Move on to feature engineering. And as you can see here, it pretty much just lets you know that the feature engineering is on the strategy, the rounds and the bins and the preview rows, as well the auto feature engineering summary, the transform feature preview, and the feature engineering details as you see here. And I want to touch on an important page, in my opinion, or I think everybody would agree, is the actual federated learning aspect of my dashboard. And this, as you can see, shows the 4 institutions, the boosting rounds, and the threshold. And this is the architecture. And I just want to kind of give you an explanation of federated learning for this dashboard. Each institution acts as a client silo. Training is performed with true federated XGBoost logic already in the app. The clients contribute summary statistics / gradients, not raw student rows. The server builds the global boosted model from aggregated information. The dashboard shows the client contributions, round behavior, and privacy guardrails. And as you see here, you have the training rounds and the global model updates over rounds. And you can see the round of global RLC, global accuracy, feature, threshold, and gain. And you have the client silos with each institution, the amount of records, and the institution gradient / statistics chart. And the privacy guardrails, which just basically lets everyone know that the privacy is in play and it is doing what it's supposed to do. And I'll move on to the risk prediction page here. And as you can see from here, you have the accuracy, the F1 score, the RLC, and the cases. You have the decision threshold, the operating confusion matrix. There's an executive reading guide. I'll skip past that for time. You have score distribution, class separation, and you have a portfolio review. And what I want to basically touch on in this review is basically there's an added level of security for the student by providing a case ID that doesn't identify who the actual student is. So only the advisor and maybe potentially the student would know if they needed to know, but they may not know as well. So this is just an added level of protection to protect the student. And I'll move on to social determinants. As you can see here, you have financial strain, caregiving responsibilities, mental health pressure, work hours per week, and commute minutes. And you have the advisor triage workspace, and you have the select case, which I kind of already mentioned that, but this is, of course, an added level of protection for the student and their information. The risk probability, the institution that this case is coming from, the level of risk. There's a advisor script ready to use. And then you have the top actions or the concrete next steps an advisor can take, resource referrals, and the privacy integrity. And this is the last page with the top global features under explainability. And that pretty much is my dashboard. So I thank you for allowing me the time to share. And this is the end of the tour. Have a good evening. And that's my presentation. Thank you very much.
So any quick question in 1-2 minutes? Otherwise, we will move to Jessica.
You mentioned a combined model. Was that referring to combining synthetic data and the real data, or?
Actually, what I did, Dr. West, is I had those 2 data sets. So I took the the academic performance and retention data set and the student management data set. And that's how I was able to come up with the 0.870.
Oh, okay.
Yes, and I combined those 2 models to get, yep. And then what it was, Dr. West, is the synthetic data set was already built in. So when you first pull up the model, then it automatically would train based off of the synthetic data set. But in order to add those two other data sets, I'd have to go to that data mode button I was showing you, and then would have to upload from there and then retrain the model.
Okay, thank you.
Any question? So, okay. Congratulations, Brian.